Welcome to Calculus. We conquer our fears and flex in the face of adversity. On this episode, Stevenson will demonstrate
You may be wondering, can use substitution work on definite integrals? And the answer is yes. Yes, it can. So let me show you. The first step is still going to be the same. You have to figure out, well, what's your u, so what are you going to keep, and then what is going to be the result of the derivative, i.e. chain rule. So if you look at this, hopefully you recognize tangent needs to be u, because the derivative of tangent is secant squared. So let's get that set up here. At this point now, if we weren't doing a definite integral, we would go right into rewriting our problem and we'd be good. But we have bounds to worry about. Here's the thing. These bounds only work when the function, the integrand, is in terms of x. We're going to change it in terms of u. So what that means is we have to also change the bounds. Here's how you do it. We're going to take each bound and individually substitute them into our u function. Well, this means we're doing the tangent of 0 and the tangent of pi over 3. Well, tangent of 0 is just 0, if you remember our unit circle here. So 0 divided by 1 is 0. Okay, let's talk about pi over 3 though. Pi over 3 is this point right here. Sorry, that's a 3. So we're going to do root 3 over 2 divided by 1/2. That means we get root 3 over 1. So these are our new bounds. Now, I recommend write them in this order where it's upper, lower bounds, because if you notice, it's going to set these up beautifully for when we write our integral. So we're going to take this now and rewrite our integral. Notice on our du, there was no additional constant or coefficient that was generated. So we literally are just going to write u du. Look how easy that is. Now, what are our new bounds? 0 and radical 3. Do you see why I suggest writing it in this order like this? Now, it just lends itself beautifully to how you can do your integral. At this point, what we're going to do now is the antiderivative, and then following the fundamental theorem of calculus, we're going to actually evaluate this all the way through to get our answer. Here's the thing though, we are not going to substitute tangent back in. We get to keep this in terms of u when we evaluate root 3 and 0. Why do we not evaluate or put tangent back in? Because we've changed the bounds to align with u. Notice there's no plus c in our answer here. Why? Because it's a definite integral. So our number, or our answer, is a number. Let's look at another example on how we can use u substitution with a definite integral. Now I want you to look at the structure of this. Have you figured out what u should be? Well, if you remember the cotangent example I gave you, you're probably already realizing we should rewrite this. Okay, so let's do some tests over here. If u is x, then du would be 1 dx. Well, that would be u, there's du, but we're not taking to this account, are we? Well, that can't work. Okay. Well, what if u is x squared minus 4? Du would be 2x dx. Oh, look, x dx. That has a 2, we can move the 2. That's going to work. So let's use that. So this right here is going to be my 1/2 du. This piece is u. So it's going to be 1 over u times my half du. And we'll just move the half out to the front. But remember, this is a definite integral, so we must change the bounds. So take the existing bounds for the function in terms of x and evaluate them in u, because we want to figure out what do those bounds mean in terms of u. We now have all of our pieces, so now we can rewrite our integral. Now let's use our antiderivative rules. Hopefully you can look at this. This is 1 over u, and hopefully you recognize that it is natural log. So now I'm going to rewrite this down here using these bounds. So to get my answer here, what I did is a log property, and I wrote the property over here for you.